Now we're going to turn to one of the beginning points of the idea of control. This is the concept of self-inspection and mistake proofing. In Japan, we see them, a couple of quotations will give us some positioning about what do we do about potential failures that are critical in our process. Taiichi Ohno said, "Waste hides, disclose all mistakes in the process." And Shigeo Shingo said, "The causes of defects lie in worker errors, and defects are the result of neglecting those errors. It follows that mistakes will not turn into defects if worker errors are discovered and eliminated beforehand." So there's a process. First of all, they recognize that all people make mistakes. But a mistake does not necessarily have to have a critical problem that's created by its work. So a mistake turns into an error when it affects someone else in the process, or it goes beyond the local work that's being done. And an error turns into a defect when it leaves the company and it affects the customers. So the idea is what we have to do is manage the opportunities for mistakes and keep inadvertent mistakes from happening. The way we do that is we go back to the measure phase, and we saw there we had a failure analysis and risk analysis discussion. And in the process of doing that, we did what was called a potential problem analysis. And if you remember in that process, at the right-hand side, after we had talked about the potential causes of the problems and we'd understood the severity and probability of occurrence, we had an identification of the current controls. And the question is, are the current controls of our process capable of preventing those mistakes or inadvertent mistakes from happening? And the way we go about dealing with those is we then convert those potential problems that we have not been able to eliminate from our process during the analyze or the improve phases. We convert those into a control plan. And we understand how we're going to monitor, how will we measure those potential errors or mistakes and keep them from happening. So mistake proofing is what's called poka-yoka. In Japanese, yokaru means to avoid, and poka means inadvertent errors. Now originally this was called baka-yoka, which means idiot proofing, but somebody thought we shouldn't really be calling the workers idiots. So the idea was changed to poka-yoka. This was developed to create what Dr. Shingo called zero defects. And so the idea was we would mistake proof the process to avoid inadvertent errors. And there were a couple of things involved. One was source inspection, 100% inspection, immediate corrective action, and then the use of mistake-proofing devices. And as we'll start seeing, this is definitely an area where industrial engineers have an opportunity to work. So Shingo identified three types of inspection. Judgment inspection. Is this good quality or not good quality? So that methodology for inspection was proven not to be effective, because I can make a judgment, you can make a judgment, and pretty soon what we start seeing is we're making inadvertent mistakes. Informative inspection is where we're using data collection and we're trying to understand based on that what's going on. So this can be statistical process control, which we'll talk about in a little bit, or self-checks. And self-checks occur when you take a look at 100% of your work and you reflect and evaluate, have I actually done this right? Traditional SPC uses a sampling method, but in the Japanese system, everything is checked by the individual. This is sometimes also called source inspection. So this is trying to determine before the facts whether the conditions that we have in the process are ready for high quality production results. And will they actually create those results on a consistent basis? So self-checks and successive checks are a combination of ways to go through the process step by step and understand, have we done the right work? Am I delivering the right work? Did I receive the right work? Am I doing the right work? Am I delivering the right work? And this series of operator checking is about the process of understanding the quality of the work we do. It's the self-monitor process, which in Japan they call hansei, self-reflection. And it's part of what they call jisukanri. Jisukanri is the process by which each person exercises self-control over the work that they do to produce a quality outcome. And so we see in a traditional system, inspection occurs at the end of the line. And so if we don't have an immediate or intermediate type of inspection process occurring, we wait until everything has been done. And now if we have a problem at the very beginning, we have to go and do all of that work in a rework process. And maybe that's not possible. So we end up scrapping product. If we have a successive check, then I understand as I'm doing the work, do I have a problem? And that then becomes the least expensive way to catch a problem and correct a problem as we're going through things. So source inspection also relies on the use of what we call these poke-yoke inspection devices. Now, these are devices that are meant to keep defects from becoming errors, because defects are the result of errors. That's what escaped to the customer, and errors are the cause of defects. So we start taking a look, and in Japan they started studying what are the most common types of errors. So we skipped a step in a process is one. We didn't do the process step right. We had an error in setting up the job. We missed something in the process itself, like a missing component on a printed circuit board. Maybe we put the wrong component in, or did the wrong task, or maybe I did an incorrect job, or I made a mistake. Maybe I measured things wrong. Maybe there was a problem with the tooling or the equipment, or a defect in one of the components. So all of those are common sources of errors. We also have some human errors. Forgetfulness. I forgot where I'm going, so I went someplace else instead. That's a bad joke I use sometimes when I'm driving someplace and I don't know where I'm going. And all of a sudden I realize I should do something about this car. I'm driving it. Maybe I should go someplace else. Well, forgetfulness is one thing. We're not concentrating on what we're doing. But we can also have errors due to misunderstanding. I didn't know where I was supposed to meet you, so I did go someplace else. Or maybe errors in identification. I can't read the map, or I met it and I went the wrong place. Or errors in an untrained worker. I'm not very, comfortable with the car, or I'm paying more attention to the car than where I'm going. Or maybe a willful error. I don't want to go that way. I want to go this way, and that road doesn't take me there. I can have an inadvertent error also because I get tired and I fall asleep. And the next thing I know, I'm on a ditch in the side of the road and I never get where I'm going. Errors also could be due to a delay in decision making. So I'm going someplace, and what I find out at the very last minute is I'm supposed to be someplace else. And then we also can see errors due to lack of standards. We don't interpret things the same way. So if we're talking about distance measures, for instance, and I talk about miles in America, I talk about kilometers in Europe, and in China, until recently, you talked about li. So if you're talking about distance, how do you get everybody calibrated to the same thing? Maybe we have a surprise error, something that happened we didn't expect. Or there's an intentional error. There's some sort of sabotage, but that's actually the least common type of problem. Many times we find when we study errors that there's a red flag condition. So a red flag condition is when somebody makes this type of mistake, the error will happen. And when that error happens, the defect almost always happens. In other words, it's like a chain reaction where it rapidly moves from one state to the other. And we find out is those things have to be protected against most particularly. And particularly if we look at this from a management perspective, we can apply what's called the rule of tens. If I catch an error at the source, it's the least expensive way to fix it. If I catch it at the end of the production, I've now converted the mistake into an error for the production line, and that costs about 10 times more than if I caught it at the worker who'd made the mistake. But if I take it outside the factory, and it's now been packaged and shipped, and it's now opened by the customer, it's going to cost 10 times more to fix that error. And if the customer has now got it in use, it's been installed, and they're using it, it costs 10 times more. That's 1,000 times more than if we caught it at the source. So, zero quality control is talking about several things: source inspection, successive checks, self-checks, and 100%. What's it doing? It's trying to prevent the errors at the source. If it can't prevent the errors, it will try to mitigate them, make sure that it's not as strong an effect. And if it can't mitigate the errors, what it will do is it will have a detection system that alarms. So the way prevention systems work, it shuts down the process. So maybe I have an infrared device that reads, my hand is going in here, it's not safe, and it shuts down the equipment. Maybe I have a system that will control, and so when the temperature rises and it gets too high, it will control and it will reduce the temperature. Or maybe I have an alarm that will go off and say, something's wrong, now you've got a warning. So all of those are different types of devices that can be used. As an industrial engineer, you'll see that there are many different types of sensor systems that you can design into factories. Limit switches, proximity sensors, laser displacement systems, vision systems, computers, timers, ultrasonic sensors, and all sorts of process measurements and different specialty sensors that can be used. And the idea is those can be used as either automatic triggers or as an operator-reliant trigger where you get warning and then the human has to intervene in the process. So as we're looking at this idea of mistake-proofing, we see there are lots of things that we can do. Even when we go into the non-manufacturing environment, we're looking at the service standards. So sometimes we can have redundancy. Maybe we're going to use color. Maybe we have counting. Maybe we combine tasks together. Maybe we have eliminating, self-elimination where mistakes eliminate themselves, like in a feedback performance. Or if you have broken pills that don't roll on a production line, and you have then the systems rolling, so all the broken ones confess they're broken because they can't actually get to the next phase. So all of those are different types of things. The whole science of design for manufacturing and manufacturability and assembly is all about mistake-proofing. It's about how do you present a set of parts to an operator in a way that can only be assembled one way. So this is an overview of the concept of mistake-proofing poka-yoke. As you get into each process, the question you have to ask yourself, and a good reason to engage operators in this discussion is, how can we prevent those mistakes from coming back and hurting you? And let the operators have their creativity in the process. And you'll find many times there are very small things that can be done to create control over our processes and create a way to safeguard our process work from all of those things we saw as opportunities for failure or risks for non-performance. Thank you very much.